Thank you so much for having me here. Today I'm going to be talking about intergenerational correlations in longevity. And this is joint work with Sandy Black, Nolan Pope, and Joe Price. So what we're going to do in this paper is that we're going to be interested in how correlated longevity or age of death is across generations. We're going to think about longevity as a summary statistic of lifetime health. And we have substantial evidence that objective measures of health of individuals while they're alive are very predictive and correlated with longevity. Um, why longevity is interesting is because it's a large component of welfare. So there are many studies that have found this much. So a study by Jones and Klenow recently kind of estimates the gains from welfare associated with changes in longevity. And these gains are very large and in many ways comparable to gains in income. And other papers in the past has found as much. Individuals' willingness to pay for longevity extensions is extremely large. Longevity is also kind of determined by other aspects of individuals' life, so education, income, or at least is correlated with. And so we're going to think of it as is a good measure, not just of health, but of welfare in general. You know, it's not a perfect measure, but it's a good measure. Um, and then we're going to talk about what the possible mechanism underlying these relationships are. This text is going to be very descriptive, so we're just simply going to start by looking at kind of does this relationship vary based on where you live, the time period you were born at, or individual characteristics. And we're going to try to compare intergenerational correlations in longevity to other standards measures that have been used in economics, like intergenerational correlations in education, occupation, or income. So briefly, what we're going to do is we're going to compute these intergenerational correlations using newly available data from family trees that comes from Family Search and that is matched to census data. So we're going to start with the 1900, 1910, and 1920 census as a base. We're going to take everybody who is observed as being alive at that point in time, and then we're going to match those individuals with family trees from Family Search. So I'm going to talk a little bit more about that, but that allows us to know when an individual was born, when they died, and the same information about their siblings, about their parents, about their grandparents, and about their kids. So if the tree is complete and if we are successful at matching people, then in principle we can observe a lot of information about how long individuals live and how that is related to how long individuals in their family live. We're going to have a very large sample of over 8 million observations. And so that's going to allow us to investigate heterogeneity in a pretty granular way over time and space and other characteristics. We're going to also then compare the intergenerational correlations in longevity to sibling correlations in the data. And we're going to compare these correlations to other measures in SES using siblings. So what's the contribution to the literature here? Well, the economics literature has not really focused on longevity as an outcome of interest, and it has instead focused on economic outcomes, well, as I mentioned before. So there's very large literature on intergenerational correlations in education, occupation, family income, earnings, and what we think is that longevity is a good summary measure for all of these. But in addition, longevity has other advantages over these measures. So if you wanted to investigate health, you could look at other health measures. A lot of health measures are quite partial. So you could look at conditions that individuals have, but you know that those only give a partial overview of how good health of the health status of individuals. Alternatively, you could look at things like self-reported health, and those measures are good indicators of health and do predict longevity, but they have a lot of challenges because they are based on self-reported answers in survey questions, and they're typically categorical. So we need to do a lot of work to kind of convert them and make them comparable over time and space. Um, Compared to economic measures like income or occupation, the advantages of using longevity are multiple. We can observe this measure equally for men and women, and so we're going to be able to say something about how those compare. That's not the case when we look at income or occupation. And for many time periods, education might also be not so comparable. There are some advantages of using longevity compared to income or occupation, in that we don't have to think about how to make these comparable over time, or over places or over ages. So a non-trivial amount of work needs to be done to adjust income for differences in cost of living, or adjust occupations for what they mean in different points in time. And even when you do that, you still have to worry about the fact that there's substantial age profiles in the evolution of these measures. And so comparing income at age 30 or 40 or 50 has different information. Whereas we're just going to look at how long a person lived. So that's very transparent and kind of easy to compute. And so it has some advantages. And we're also going to be able to look at more than one generation.
Sorry, Adriana, just
Yeah.
very quickly, do you know how big is the genetic component of longevity? Do we have any idea?
We're going to talk about that in a second, okay? That's going to be an important part of this discussion. So I was just about to talk about this. In demography, and I guess I was, when I first wanted to do this, I was very excited. I'm like, I haven't seen people in economics do this. And then I discovered that, in fact, there's a very old literature going back to 1898 of people in genetics that has estimated the correlation in longevity. And their objective was precisely to establish the genetic component of longevity. And so I'm not going to talk about a lot of those papers, but in the paper, we have a big table that we've collected with all the studies that have been done in there looking at these questions. And many of them take advantage of similar samples where they have, for instance, data from aristocratic families, and then they use that historical data from, say, the British aristocrats to investigate that. So that was the first study that was done there. So relative to what I'm calling here demography, or you might think of it as genetics, what we're going to be able to do is establish the representativeness of this sample. And so most of the previous studies kind of have convenient samples because it's hard to kind of get these data. And so they have aristocratic families, or, families for whom there are records. And so what we're going to be able to do that we think is valuable is say something about who is in this sample and who is not in this sample, at least for the United States. We also going to have some advantage that because we're using the census and these family trees, the family trees has grown very substantially in the last few years with the help of the internet, relative to older studies that relied on genealogical hand collected data of sorts. And so we have a very large sample. And we're going to be able to also shift the focus a little bit by comparing longevity to correlation in other economic outcomes. So I can come back a little bit to that literature, but just to give you the punchline a little bit, the intergenerational correlation in longevity in these previous studies, it depends exactly on how people measure it, but it ranges somewhere between 0.05 and maybe 0.025, and it's low. And what we're going to find here is very similar to what other people have found in the past, despite the fact that the samples come from different times and different places and different populations. So we're going to get kind of confirm what they have found in our sample, and the number we're going to find is low. And to kind of come back to your question, our findings so far kind of suggest that the genetic component of this correlation is rather small. So I'll come back to that and see if you find that compelling. Okay, so let me talk a little bit more about the data. So we start with the census data. These are complete censuses in the US. We're going to focus on everyone that was born between 1880 and 1920. And we're also going to link these individuals to the 1940 census. So the advantage of people matching individuals to the 1940 census is that the 1940 census is the first census that collects information on income and education. Prior censuses only collected information on occupation in every census. We're going to restrict people to cohorts born between 1980 and 1920. Think of the baseline sample as the children, and we're going to kind of pay attention to people who survived to age 25. So this is an interesting question because, as an earlier speaker talked about, we're going to, in some sense, we're not going to be able to say anything about people who don't have children who made it to age 25 in these censuses. And so we're going to restrict attention to those individuals. In part, it's because we don't really know how to deal with people who didn't have children, although, I'll be studying the earlier paper carefully, but also for comparability. Almost all the studies done in genetics made the similar restriction, and almost all the studies done in economic makes similar restrictions because they want individuals that have completed schooling or individuals whose earnings are kind of representative of their lifetime earnings or occupation. So we're going to focus on them. We're going to take these individuals and then match them to family trees. And let me speak a little bit about that. This collection of family trees is the largest collection of these such trees in the world. As of right now, about 1.3 billion individuals are represented there. Where does the information in these trees come from? And the answer is that it comes from a variety of sources. Some of it is individuals who are doing their own genealogical work, and they enter the information into the database. When individuals do this and they create their trees, there's a substantial amount of variation in how good the information is that they provide. Some individuals are very careful and attach a lot of records to document the accuracy of the information. And so some of them will have birth records and death records, or records from other places like schools or obituaries that kind of confirm or show where the information comes from. Some people just put down what they know. The information in the family tree is often complemented or checked by genealogists and also by machines and programs that are constantly kind of updating information and making suggestions about how to improve the information on the tree. So an issue always with this kind of data is going to be, is this data kind of accurate and good? And I'll try to address that question later on. I will say that it's the only source of data that we know of that can allow us to do this kind of long-term analysis of longevity across generations. And in some sense, in spirit, is similar to what was done more than a century ago. It just uses what people know about their families. So we're going to match people in the census to the family tree. And so that step also kind of presents a challenge, which is that not all individuals might be found in the family trees. So we're also going to think about what kind of selection happens here. So the sample we're going to be working on corresponds to about 8.6 million individuals that for whom we know when they were born, when they died, and we have the similar information for the parents. And then given everything that I said, I kind of want to talk about these two key issues in the data construction. Who is represented in our sample, and is the age of death accurate? So we did a comparison here between the census sample that we start with and the data that was matched to the trees. So some notable things to know here. So kind of strengths and limitations of our data. Women are very well represented in our data. So they're about 45%, whereas in the census sample we're 44%. So this is a great advantage compared to many other studies that we can do a very good job at looking at them. On the other hand, we can do a very bad job right now at looking at non-white populations. So Black populations are, in historical work, well known to be difficult to track for many reasons, but in doing these matches, individuals who switch names, cross records, individuals who, for instance, might be illiterate and have errors in their spelling or don't know when and where they were born are very difficult to match. And this is partly the reason we think why some populations are poorly represented here, but it's very noticeable that we only have less than 1% of records correspond to Black individuals, whereas in the census, they're about 13%. There's a similar issue with individuals who are immigrants who are underrepresented in our sample. And also, interestingly enough, the different regions of the United States are not equally represented. So the distribution in our sample is tilted towards the Midwest. And that's because Midwest states like Ohio actually have really good records, like birth records and death records going back in time. And I suspect maybe those populations are also maybe more genealogically inclined. I'm not sure that that's true, but the fact remains that they're more represented in our sample than in the census sample, whereas the Northeast region of the United States is underrepresented. So in the middle column over here, we show kind of how well we can do if we try to reweigh the data to kind of address kind of this geographic imbalance. We also have a little bit of a cohort imbalance where our data is tilted towards more recently born cohorts relative to those in the sample. So we're going to try to reweigh the data for account of that, to account for that. And we do okay when we do that, but it's not a perfect correction yet. So these are the limitations of the data that we have right now. And we're working on trying to extend the sample for the minority populations, but we're not going to present anything by race today because we simply don't think the results for these subpopulations are to be trusted. So the second question is whether this data is reasonable at all. And in here, what I'm showing are some figures that we did that compare the survival rates of males and females separately for two cohorts for which comparable data exists in the United States. So what we do is that we take a look at the 1900 birth cohort, so people who were born in 1900. And for that cohort, the Social Security Administration has provided cohort life tables for the US. And such tables also exist for 1910. And so these data from the Social Security Administration are supposed to be representative of the United States. And we can kind of compare how our data lines up with theirs. And for the 1900 cohort, we can see that the survival curves that we have are very reasonable, but our data, our cohorts are slightly, have a larger life expectancy. So the red survival curve is above the blue survival curve. That in 1900 for males corresponds to a difference in life expectancy or cohort life expectancy of 2 years. By 1900, that difference is about 1 year, and the same is true for women. So individuals in our data live longer, and we know from what I just showed before that individuals in our data are positively selected in terms of, for instance, race and immigration status. And also because of the process of how the data is collected, it's likely that they're positively selected on other dimensions like literacy and education. But these differences are not super big. And I should also mention that it's hard to line up the data because the Social Security Administration data does not actually come from the US population. The US does not have a complete vital registration system until 1933. So in 1900, only a few states had registration systems. And so the Social Security Administration computations themselves use weights to account for the fact that only a few states are included. So given these considerations, we feel like the data looks pretty reasonable, and that the differences we observe are the ones that one might have expected in ex ante to observe. Something else that we looked at, I'm going to show for time, is that if we plot the distribution of the ages of death, we don't see a lot of evidence of things like age heaping that would suggest that the data is of very low quality. Nevertheless, we can talk more about the data quality later because this is kind of a crucial point for what we're doing. So what do we see in this data? And so here I'm plotting the cohort life expectancy in these matched sample that we're using. And the blue line in dots shows the evolution of life expectancy for cohorts born 1880 to 1920 for women. And we see a pretty substantial increase in life expectancy throughout the period. And then we see that, well, women lived longer than men in all of these birth cohorts, and the gap between them started being rather, small couple of years. And, by if we look at the 1920 cohort, this has almost doubled. And this is consistent with prior research showing that there is an emergence in the gender gap in life expectancy that starts sometimes in the late 19th century, and that these differences between men and women kind of grew very substantially throughout the first half of the 20th century. We also see, interestingly enough, that there's some kind of declines in the life expectancy of these cohorts born towards this period. And this may be consistent with other historical research showing, for instance, declines in height and possibly the effects of what happened after the Civil War. So it's kind of a surprising thing, but we do see that starting sometime in the late 19th century, the life expectancy of male cohorts also starts rising substantially. So these are broadly consistent with what we know, although I should emphasize there are no cohort life expectancy measures for the United States for all of these periods that are representative. So this is a value of our data that we can even plot these numbers. So I'm going to start with something that I call the data generating model. I don't want to even call it a model given like the serious models that we were, talked about earlier here. But this is just to kind of fix ideas, just very simply on what we think might be generating these correlations. And this is a data generating model that will allow us to make some simple predictions and is in the spirit of the models that are written in genetics. So we're going to think about the age of death of an individual born to in a given family in a given cohort and time place and of a given gender. And we're going to say that life expectancy is a function of, and here it's linear, of the genes that they receive from each parent. So each person receives half of their genes from their father and another half from their mother, but there are mutations that occur each time. And so there's going to be some variation that occurs. So you receive a random half from your mom, from another random half from your mom, and some of those change along the way. And then we're going to have environmental factors that affect a person's longevity. So consistent with the literature, we will say the quality of the air and of the water are going to affect your health. The technology that you have available to cure yourself or to prevent disease is also going to matter. So there's going to be a number of kind of factors that depend on the time and place where you were born that are going to affect your longevity. We're going to allow for gender specific effect, and that is going to, oh, I missed that over here, that we're going to think of this effect as being partly genetic, partly hormonal, and partly social. And so this is just simply going to allow for life expectancy or health differences to be systematically different across the genders. And then there's going to be a component that's going to be due to socioeconomic status. So we think that individuals that have higher education, income, wealth, who are higher ranked in society might be able to purchase goods and services, live in places, find spouses that are different, and that these factors are going to allow them to live longer. And this is in some sense almost like a decomposition or something, where what we're trying to do here is to account for what is known in the literature as affecting life expectancy. Now, there is some debate in the literature, of course, about the extent to which any of these things are causal, but we're going to imagine that the data is generated like this with, of course, some transitory component as well. And I'm not going to make any statement about that error term. I'm just going to say that there's a random component there. Now, just right then and there, of course, this is going to be a very strong set of assumptions that we're making here. Obviously, we're stating that this is linear, which it need not be. We are not allowing for interactions, and that is almost surely incorrect. So we, the most recent knowledge leads us to believe there are important gene-environment interactions. There are almost surely also some interactions between gender and the environment, and there are very likely also interactions between SES and the environment, or SES and the genes. And so this is a very simplified model where we only are allowing for these first order effects. This is, of course, also just a data generating model that is not taking into account any behavior or any optimization that may go on. And so this is just a first step, but the reason this is interesting, and the last thing I want to say is we in here are not allowing for the lifespan of the parent to have direct impact on the lifespan of the kid, except through the common components that are either the socioeconomic status, which is common to the family, or the fact that the fathers and so parents and children live in the same place, or they share the same genes. So that's also something that you might worry about. So why is it interesting to write this model? The reason it's interesting to write this model is because we're going to be running some regressions, and we kind of want to know something about what those coefficients are going to capture under the null hypothesis that this is the data generating process. And the predictions of this model are that if we run a regression of the children's age of death on the parents' age of death, then that coefficient, which we're calling a correlation, although that's not quite appropriate, but we're calling this the intergenerational correlation in longevity. So that regression coefficient is actually going to capture multiple things. It's going to capture the genetic component, including an assortative mating component among the parents. It's going to capture the environmental component that is common to both parents and children. So if they both live in the same place and that place hasn't changed over time, that's going to be picked up by this regression coefficient. And then it is to the extent that they share the same socioeconomic status, that's also going to be picked up in this regression. Other predictions of this model that are interesting is that if this environment is stable, and so the environment isn't changing over time, and it's shared by the parents and the kids, then we get this very nice ordering in the data. So we would predict that a few things are going to be true. The regression of a son's life expectancy and a father's life expectancy is going to yield this coefficient beta, and that coefficient is going to be the same as the regression of a brother's life expectancy on their brother's life expectancy. And that coefficient itself is going to be smaller than if we regress a twin's life expectancy on their twin's life expectancy. So we're going to have this ordering: the twin coefficient, the twin correlation greater than the brother correlation, which is the same as the father-son correlation. The father-son correlation is going to be greater than the mother-son correlation, and that's going to be greater than the father-mother correlation. And sorry, I keep saying correlation, but it's really the regression coefficient. We're also going to see that if we do a regression of the kids' life expectancy on the average of the parents' life expectancy, that coefficient is going to be larger than if we just look at the life expectancy of one parent. And we also have the prediction that the regression coefficient of the kid on the father will be greater than of the kid on the grandfather. So we're going to look in the data to see if these very basic predictions fail or hold. And if they fail, then we're going to try to see where they fail. Okay, so that leads us to this regression, which I was just talking about: the age of death of the kid and the age of death of the parent. We're going to do this conditional on surviving to age 25, and we may or may not include covariates. So the basic model that we're going to have is going to include birth cohort dummies for the parents and for the children to account for the fact that I just showed you that life expectancy was changing. So the environment is not stationary to begin with or constant. And so we're going to run these regressions with these basic cohort dummies and nothing else. I'm going to show you what happens if I don't include cohort dummies, and I'm also going to show you what happens if I have other controls. Now, you may also object to this functional form, so we're going to check what happens if we do this in logs or in ranks. We're going to look to see if this linearity assumption for this equation holds, and we're also going to see how much it matters to have a different cutoff for different ages. So here's our main results of by gender and outcome. So the outcome is just different kind of transformations here. So if we look at father-son correlations, these correlations about 0.1. It's actually quite surprising that if we do it in percentile, so if we do a rank regression, we get a similar number. If we do it log, we get a similar number. This column over here shows you what happens when we use our weighting scheme to try to become a bit more representative of the population. And this number becomes a little bit bigger, kind of already suggesting that there may be some important differences in space in these correlations. What you also see is that the correlation between the father and son is greater than the correlation between mother and son, and that's as the model would predict. Then when we look at the correlations between mothers and daughters, those are similar to the correlations between fathers and daughters. And you see that for almost all of these measures that we look in here, they're pretty stable, kind of regardless of how we estimate the model, which is kind of surprising, although some of these numbers are somewhat sensitive here. Also, as the model predicted, when we look at a regression of the sons on the parents' average life expectancy, those numbers are substantially larger, almost twice as large. And the reason why they're almost twice as large is because the correlation between fathers and mothers' life expectancy is rather small, only 0.04. So there's some assortative mating where people who live long marry each other, but it's low in this sense. So now let me show you what happens when we do control. So the first thing that I'm going to show you is that despite the fact that there have been large changes in life expectancy over time, these cohort controls matter very little. And so here you can see the father-son correlations with controls for these measures and without controls, and they are almost identical. And if instead of regression coefficients, I just do a correlation, then I get an even smaller number. That is, 20% smaller, still kind of within that range of like 0.1. And the same is true for daughter and mother correlations, which tend to be a bit lower than the correlations for man. If I show you some additional controls, so let's say that I take the father-son correlations, and now in this regression, I add state of birth of both parents and children, or I add controls for race and birth order, you can see that almost nothing happens here. So the same would be true for our other regressions. So this is seems to be not particularly sensitive to our specification, but I'll come back to this a little bit later and thinking about adding even more controls. So this model assumes linearity, and how good is this assumption? And the answer is it's not terrible in levels, it's pretty good in ranks. So in levels, you can kind of see this is the slope of the regression that we've estimated. It gives us a coefficient about 0.1 for father-sons. The linearity assumption breaks down at the bottom. So there are fathers who live short lives that have sons that have lived very long lives. And that's where this is somewhat nonlinear. It also breaks down a little bit at the very top. We can see that if we do a rank transformation, kind of similar to what happens when you look at income, then this is really, really linear, except again for the very bottom and the very top of the distribution. So that assumption is okay, particularly in rank. The other question is how sensitive these results are to truncation. So if you look at the literature in economics, people choose different truncation points. If we look at education, people typically restrict to age 25. If you look at incomes, people typically restrict to age 40. In papers that have looked at things like self-reported health or wealth, they look at older individuals like 50 or 60. In the literature that looks at genetics, so the genetics literature, they have also done different truncations for different reasons. So one reason they have argued that we want to truncate at older ages is that a lot of the causes of death among prime age adults are kind of unrelated to health. So the hypothesis among the geneticists has been that the correlations or the regression coefficients that we obtain when we truncate at, say, age 60, they were expected to be much higher. And so their hypothesis is that the role of genes is best uncovered if we look at the likelihood of living very long of a person as a function of whether or not their parent also lived very long. What's kind of surprising in this figure when we first plotted it is that, in fact, we don't find any evidence that that's true. And in fact, we don't find any evidence that the truncation that we choose is particularly important. So we do see a bit of an increase for mother-daughters in the correlation. For father-sons, this correlation is pretty stable. And if we look at the average, it kind of, it goes down a little bit, but it is not dramatically different.
Professor, you have about 2 more minutes.
Yeah. Okay. So, okay. In my watch, I had more minutes. Sorry. Okay. So, one question that
we don't need to have if you need a little bit more, do it. You're the judge of the presentation.
Okay. Sorry. I started my time watcher when we started, but okay. Okay. So, you might ask now, I said that this coefficient is going to capture genes, environment, and SES, and can we parse this out? So we've done a couple of things to try and do that. And one of the things that we did is with the 1940 census, take a look at the father-son correlations and see, well, what happens if we control for a measure of SES? So we have the child's education, their income, and their occupation. And what you can see here is that the answer is that nothing happens. And so these measures, education in particular here, those actually predict life expectancy in a correlational sense, and it is statistically significant, is just not affecting these coefficients particularly a lot. And you know, these measures, which are the 1940 SES measures, also kind of don't matter very much. And the results are similar for women. So SES doesn't appear to be the mechanism here. So the next thing that we might look at is adopted children. So many people have used this in the past in thinking that adopted children don't share any genes with their adopted parents. And so if we run these correlations, whatever we find has to come either through common socioeconomic status or common environments. And what we find is that if we compare our full sample over here with the adopted children sample, which is much smaller, the adopted children sample yields coefficients that are smaller, but not by much. Now, we don't know if adopted children are adopted by extended family members or others. If we make the strong assumption that adopted children are genetically unrelated to their adopted parents, then that puts an upper bound on the genetic contribution of 30%. So we could say that the correlation in longevity that's due to genes is only 0.03 and accounts only for 30% of these coefficients that we estimate. If we could make a different assumption here, that would increase the genetic contribution a little bit, but it would still imply a genetic contribution that's rather small. The next thing that we do is looking at siblings and twins correlations. So we look at people in the 1940 census, and in the 1940 census, we can have the education and income of an occupation of individuals, and we can compare then what happens to the correlations in lifespan to the correlations in these other measures. I'm only showing education because occupation and income are not available for many women. And so the samples drop a lot for them. And so here, what's interested in here is that, you know, the lifespan correlation here for siblings is 0.138. And it is smaller than the correlation for twins, which is as the model predicted. We also see that these numbers in the same sample, the brother-brother correlation is substantially smaller than the brother-brother correlation in education. And if I showed you the results for income and occupation, they would be somewhere in the middle over here. So regardless of the economic measure that we use, what we find is that these lifespan correlations across siblings are substantially smaller than the socioeconomic correlations in the data. Something else that's interesting is that these correlations that we estimate here for education are very similar to correlations that have been estimated by other people in the literature, which suggests that although our sample is selected, it's not so weirdly selected as to give us things that are outside of the bounds of what other people have estimated before. I'm going to take advantage of this data to show you something about grandparents. And so these are bivariate regressions, and consistent with our model, the correlation between children and grandparents over here is substantially smaller than that between fathers and sons, but it's still not zero. And interestingly enough, if we put them all in a single regression, the grandfather's lifespan still predicts the grandson's lifespan, even controlling for maternal and paternal lifespan. So this is not as predicted by the model. And so there's something else going on here. It could be that some of these life expectancies are measured with error. It could also be that the model is misspecified and something else matters here. So quickly, some sense of heterogeneity. So I told you we could investigate this. This also is kind of shocking, but when we did this cohort by cohort, we found almost no change throughout these 40 cohorts in these correlations. And this, I think, kind of explains perhaps the reason why a lot of studies, a lot of different time periods have come up with numbers that are roughly around this time, because we just simply don't see that much change in this dimension. which is also surprising. There was tremendous change in life expectancy. Okay, that's my own timer. What we see a little bit of a change on is the spousal correlations over time. So those were small on average in the sample, they were around 0.4, but we do see kind of an increase over here. What we do see is a bit more heterogeneity based on place of birth. So if you plot these correlations by cohort and we do a map of the United States, we see a couple of things. First, that there is variation in space. And second, that the variation in space is not the same for women as it is for men. And it is also not particularly persistent in that the states that have high correlations for the 1880 cohorts are not necessarily the same the states that have high correlations in the 1890 cohort, which suggests that there really are environmental differences that are affecting these correlations, and that these differences in space kind of matter, and that's an important source of heterogeneity. We did other things for heterogeneity. We have such large samples that almost everything that we put in the regression is significant in a statistical sense, but the economic magnitude of these interactions are small. So if we interact the father's life expectancy with family size, birth order, maternal or paternal age at birth, or the education of the kid, all of that stuff significant, but the magnitude is so small, it's not worth talking about. The one thing that was kind of interesting is that immigrants have larger coefficients. So for the sons, we would find a coefficient of 0.125, whereas for natives, we would find something closer to 0.1. So this again, pointing probably to the importance of this geographic location mattering substantially. And so the last thing I'm going to say and shut up is that we then look to see if the correlations in longevity are in space are correlated to the correlations in SES measures. So this kind of shows you the coefficient of a regression of siblings education under siblings education. And on the y-axis is the correlation across siblings in life expectancy. And then you can see that particularly for males, these things are correlated, although the correlation is not super high, but it's a correlation of 0.1. So it does seem like groups with higher correlations in education have higher correlations in longevity. Suggesting kind of maybe there's something like important gene environment interactions. So this is what we're working on. We don't know why this is true. This kind of suggests also that since these correlations are there, but they're small, that if we did a measure that combined measures of intergenerational correlations in SES and in longevity, these measures would kind of be much larger because there's independent contribution of each. Okay, so I'm just going to stop there and say, we thought this was surprising. This correlation is low, and it suggests that the genetic contribution is small and that most of the correlation is kind of driven by shared environmental conditions. And this correlation is low than correlations in SES, and it's low than correlations in health measures. And so Bash, I think, is going to talk about, has several papers doing this, and when they use overall measures of health of people who are still alive, they find correlations that are larger than the ones we obtain. And kind of lastly, this very simple model in some sense is a surprisingly good approximation of the world so far, except for the fact that our R-squares are really low, so there remains a lot to kind of be explained. So I'm going to stop here and just take questions.
Terrific, thank you.
Can I go, Stephen?
Of course.
So processing it quickly, like my kind of takeaway was what you were just alluding to, that the R-squareds were really low. And so I was wondering, like thinking about your data generating model, you had those, I think they were ADAs that you called the mutations in there. And so I wonder if, like, I would figure that's got to be the stuff that ends up in the error term, and that you would think potentially is extremely important, and what most of that missing R-squared might be attributable to. And I wonder if, kind of related to that, it pays to think about the parents' longevity and then the grandparents' longevity as kind of multiple mismeasured proxies of the kid's genetics. So as opposed to there being a direct effect of the parent, these things are proxying for whatever the mutations are that are going on in the child's as an adult. And it might suggest, you know, from that literature, thinking about using, let's say, like the grandparent's longevity as an IV for the father's longevity and see where that might get you. But anyway, I mean, I just like those ADAs, then that's what strikes me as important. And I wonder if there's some way to try and get at that and quantify that aspect of it.
Yeah, that's very interesting. I don't know how we would try to get an aspect on the ADA. I mean, my interpretation of this is somewhat different, which is that that basically there's a lot of randomness in this process of longevity. I mean, so we've tried to do things like eliminate wars or other kind of episodes that would kind of kill people for reasons that are not related to health, and that you might just think that add a lot of kind of random variation. And that matters a little bit, but you know, not enough to make these numbers substantially different. Not and nowhere can we get anywhere close anything like 0.5, which is what you'd see for education. So so I don't know. I don't know, but I'll try to think about the mutations question, because that's not something we've investigated deeply. I don't know how to get a handle on that, but let me think about that some more. On using the grandfather as an IV, it's an interesting question, although in those regressions, we kind of see there's a direct effect. In those kind of reduced form regressions, there's a direct effect of the grandparents on the grandchildren, even conditional on the father's life expectancy. So I'm not sure why that is. And it could be because there's measurement error, as you said, right? Like there's measurement error in the parents and there's measurement error. And so the grandfather is still picking up some of the effect that could be actually attributed to the father. But it could also just be that, well, the model is wrong and the grandparents do have still some influence, and it's not genetic because the genetic model would fail, but it's through, for instance, transmission of wealth or something else that we're not capturing well. So, you know, we have controls for SES of the kid, but we don't have controls for the SES of the parents or the grandparents. And so that could be something else that's going on there. But let me think about that some more.
A quick comment. This could be the classic issue of lack of variability in treatment. You think of in the explanatory variable for every given longevity for one generation, you're going to need a massive amount of variability in the longevity of the explanatory variables. Absent that, you're going to get very small coefficients, which you're referring to as correlations. I'm talking about the classic T ratio problem, when there's not enough variation in the regressors.
That's an interesting point, but I have to say I'm not sure, because I showed you those figures at the beginning showing big changes in life expectancy over time, and there are some very big differences in space. And if you just look at the summary statistics, and I didn't show you that, and I apologize, but the standard deviation of longevity for sons is about 16 years, and for fathers is about 12. So it's true there's less variation for the fathers than the sons, but it's not close to zero, anywhere close to zero. So I think there is kind of still substantial variation. And for the mothers, the standard deviation is 14 years. And so I think that there's almost as much variation in the life expectancy of the kids as there is variation in the life expectancy of the parents. So I'm not, I mean, to me, that seems like a substantial amount of variation. But I mean, I'll think about that some more.
How would you think about causes of death?
Sorry, about
How would you
causes?
Let's go on the other side and think about causes of death. What sort of intergenerational correlations would you moved across that, and how would that map into the life expectancy? It's just a way of trying to ask questions, trying to think more about mechanisms. To play this.
That's a good question. We haven't done much on the causes of death, but we are collecting data that will allow us to do better. So the more recent life certificates will always have it. The older life certificates, a lot of that has to be kind of digitized. And so Joe, my co-author, is making some heroic efforts in the dimensions of trying to get more records for minorities and trying to get cause of death for older populations. And so we might be able to look at that. It's an interesting question. I think one would have to write some kind of model with a competing risks hypotheses, because I think our first intuition might be like, oh, if my mom died of cancer, I'm going to die of cancer, and maybe that's what's happening. But if that was true, we would be finding maybe greater correlations here. And what has happened over time is the causes of death have changed quite substantially. So I think most of the cohorts born of the parents would die of infectious disease, and most of the children are going to be dying of things like cardiovascular disease. So I would actually posit that the correlation is going to be small also, despite the fact that we think there are important genetic contributors to these behavioral risks, but it's because of these competing risk issue, which is that, you might have a predisposition to heart disease, but if we have technology that saves you, then that's not going to pan out. Or if you die from, being in a war or something else before you are eligible for dying of a heart attack, then that's also not going to pan out in the data. So I have to think about how we write that model. So I don't have a full answer on how to think about that, but we are working on the data. So hopefully we'll be able to show something and then think about it more.
One thing just to add to that is that was really surprising to us that Adriana showed is how conditioning on age kind of didn't change the correlation. And that's kind of where we thought, okay, as you get older, conditional on living to age 50, it seems like it should be more highly correlated, because then it's like you're really getting, not these accidental deaths, not, infectious diseases, but then you're really going to be getting the heart disease, the cancer. And so it really was surprising to us that it's so flat. I mean, it's really a puzzle. And I think looking at cause of death is something we are hoping to do, because it is, I think, yeah, we've been surprised this whole time at both how small the correlation is and how kind of persistent it is across all these different specifications.
Although I should say, I keep saying it's similar to the eye, but sometimes we have this discussion, we do see a change, say, over time from 0.1 to maybe 0.85 or something. So that's a reduction of, say, 15% or 20%. So in relative terms, there is some kind of important variation even across states. It's just that in absolute levels, the variation seems to be small, and it especially seems to be very small compared to the variation that you see in SES. So if you go back and look at that plot, when you look at the correlation in SES across siblings by state, that range is really much bigger than the range that we see for longevity. So again, kind of from that perspective, it seems like small is the right thing to say, but from another perspective, maybe the variation is actually not so small. So that's something I'm not quite sure kind of how to handle.
I have a comment. So just to follow up Stephen's point about the cause of death, the Berkeley Pop Center recently published the linked 1940 census with the Social Security, the mortality files, and the nominant files. So I wonder whether you can restrict the sample to father and sons live together in the same household in 1940, so that we probably can find both of their death records. from the linked file, or restrict the sample to, or combine it with the linked census data. So if they ever lived together in the 1930 or 1920 or even earlier census, so we know that they are our parents and offspring, and they both showed up in 1940 census, and then find their death record in the mortality file.
So the thing is that the Berkeley data matches the 1940 census to the DMF. The DMF only has death certificates that are complete set records of the population starting roughly in 1975. And that's similar to the death certificates that we have. And what that means is that, you know, we do have the death certificate with cause of death for the kids. The challenge is getting the cause of death for the parents who are not in this modern death certificate bin of the death mortality file. So prior to 1975, you have to rely on state records or just family records, and sometimes even no death certificate records. And so that becomes more challenging. So I think what we're attempting to do now is look at a state like Ohio, which has had death certificates for a much longer time. So Massachusetts is another one. And then you can get a good handle on this. But it's going to be practically impossible to do a good job at that nationwide, because there just aren't death certificates. So the last state to enter the death certificate registration system was Texas in 1933 or 35. And so if you go anytime before that, the records are just really incomplete, and they don't necessarily have cause of death.
I see.
So that's really the challenge. But I think I like your idea of one thing we haven't done is we haven't restricted parents living with kids. So that's something we could do. We do know in the censuses if they're living together. We're not restricting it that way, because we're including people who are older than only people who are older than 25. And if you did that, then you'd get a very selected sample. You know, the people who live with their parents still at age 25 is a pretty selected set of people. So yeah, I don't know. It's kind of challenging. Sorry, I like your idea, but as I think about it, I'm like, I don't know if it's implementable.
I see.
Perhaps I missed it, but do you have information on occupation?
Yes, we have information on occupation. So for the children who are the kind of the ego, the baseline observation that we use, we have occupation in the baseline sample. We also have the occupation in 1940. For the parents, we would need to match them to a census record in order to get that occupation. So we can try to do that for a subset of people and see how successful we are, because the census does collect occupation going back in time. So something that we have discussed is to expand kind of our sample. The baseline sample right now is 1900 to 1920. The previous census that's available to that is 1880, 1870, those 1860, those census have occupations, and we could try to find the parents there and see how well we do. So we have some results for correlations in occupation among siblings in 1940, but not father sons or mother daughters, and we also, we haven't controlled for the parental occupation. So that's something that we could try to improve for sure. It would just require some data work.
Okay. I think, I'm sorry, Barbara, did you have a question? Or let me just see if anybody else has any final things to ask. Anyways, I thought I thoroughly enjoyed everything I heard today, so thank you. And we will reconvene tomorrow at 10.
Thank you.
All right.
Thank you. Thanks.
Take care, everybody.
Thank you.
Cheers.
Thank you.
Thank you.
Bye.
See you tomorrow.
See you.
Thank you.